thinking stuff. It doesn't look particularly different than some of the stuff we've done before. For instance, once I get this bloody, all my little gizmos are pointing the wrong way. Is that it? Okay. Where was I? Yeah. It's basically like stuff you've done, but different enough to confuse you. You're going to take a curve, and at least for today, rotate it about the x-axis. Well, we've taken curves and rotated them about the x-axis before. We've did it to find the volume. But now we're going to do it to find the surface area. So can you imagine this curve here being rotated about the x-axis? Wouldn't it look something like the pawn on a chessboard? That would be my description of that shape. We are not going to find the volume of that 3D shape. We are going to find its surface area. So can you imagine how many square inches it's got on the outside, right? Just the surface. It's called the surface area. And we are going to find it. And you say, oh, well, that's fine. You'll just tell me a formula and I'll plug and chug. And I'll probably have some really messy algebra to do, especially if there's a trig function involved. And that is true, you will. But look at the little bit that makes it sneaky. When you rotated about the x-axis, there was an x-axis formula. When you rotated about the y-axis, there was a y-axis formula, and we chose for it. But look at this. This is the bit that makes it awkward. If your curve is written in the form y equals x, so if you're told that this is y equals x cubed, and you're going from x equals a to x equals b, then the formula for the surface area is an integral, as you'd expect, from a to b, 2 pi, whatever the function is, the square root of that. Now, if I cover up all this bit, do you recognize the 1 plus derivative squared? It doesn't look much like a derivative, does it there? Do you remember that guy, the square root of 1 plus the derivative squared guy?
Yeah, from last week.
Yeah, it's the arc length formula. Can you remember a formula that went something, at least it began with 2 pi y and then had some other stuff? Remember that guy? Wasn't that the formula for the volume? It's a kind of a monster formula. It's a bit of an arc length formula and it's a bit of a volume formula. But when you put them together in this order, it's a surface area. So the surface area formula is much bigger and uglier. Right, it's got an f of x here and the derivative there, and it's integral from a to b. And if that was all it was, it wouldn't be that bad. It'd just be uglier. But this is the kicker. If this curve up here wasn't written as y equals x cubed, but x equals the cube root of y plus 4, right? Something like that, right? X equals function of y, right? X equals g of y. And it went from C to D, but it was still rotated about the x-axis, then this is the formula that you use. The integral from C to D, 2 pi y, the square root of 1 plus y squared dy. I guess I should probably draw a little picture for that. If you get a question where the curve, say, starts, well, it's going to be C to D, isn't it? So it starts here and it goes something like that, right? But you still rotate it about the x-axis. You see that there's a new formula for it. So one of the things you're going to have to do here is choose the correct formula from this pair if you're going to rotate something about the x-axis. So let's look at this guy here. Here are two, I hope, simple examples just to get this show on the road. And the first one is y equals x cubed. The x's are going to go from 0 to 4. And you're being told it's rotated about the x-axis. And so I look at the information and I say, oh, it's a y equals x cubed and it's x from a to b. So that means use this formula. So step one. Choose the appropriate formula. Now, if they had said x equals y squared minus 1 from y equals 1 to 4, but they said rotate this curve about the x-axis, can you see this guy here would be using the second formula, and the one that we're doing right now uses the top formula. Can you see how you can tell which formula to use? It depends on the way that the information is handed to you. Is it handed to you in terms of x? Use the one with the dx on it. If they tell you the information in terms of y, use the formula with the dy on it. Well, that's just the first of many hiccups. Step 2. Find the simplified form of this guy. So we're pretty much going to go through steps that involve doing what we did yesterday. Remember when we did yesterday, Friday? Remember we did arc length very often. We just figured this out. Now, if life is nice, won't this be a perfect square, or it'll be something really easy to work with, right? And it should be, hopefully. So let's see what we've got. We've got y equals x cubed. Its derivative is 3x squared. 1 plus its derivative squared is 1 plus 3x squared squared. So we have 1 plus 9x to the 4. That's fine. In this case, I don't need to do much. Would you agree that's pretty nice? I don't need to do any trig identities, for instance. Now, step 3. Use the full formula. So the surface area of this shape is going to be the integral from 0 to 4, 2 pi f of x, which in this case is x cubed, and the square root of 1 plus the derivative squared dx. Can I pause there? Are you comfortable about where all the pieces are fitting right now, where they're all coming from? You happy where this guy's coming from, where this guy's coming from, right? And that I'm using the top formula. Now, what you tend to get in these questions, there are like 3 things that can happen. The first one's not going to happen very much, but it might. That this square root here is just a number. It's like square root 17. If you see one of them, you'll see 1, maybe 2 at most. That's not the major one. The 2 major techniques are you're going to do u subs, or this is going to be a perfect square. That's the most likely things. There is a very small chance the integration by parts, but not really a major one if it happens. Look at that guy. What technique will I use to integrate 2 pi x cubed, the square root of 1 plus 9x to the 4?
U sub?
Correct. Would you agree the u sub is the guy inside the square root? So the most likely techniques that you're going to use on these when the question is, not trivial, it's going to be u subs, or the thing inside the square root's a perfect square. Now, if you differentiate this guy with respect to x, you get 36x cubed. If you do the crossover, you get 36x cubed dx. And if you divide, you get this guy. And now we are hopefully closer to the end. So it's going to be the integral. Well, let's pull the 2 pi out. Got an x cubed. I got square root of u. And I have got a 1 over 36 x cubed. And I have a du. That comes out and joins that one. So I now have pi over 18. The square root of u. Du. Would you agree that's a really nice sign when you see that? That's a good sign that the u sub's doing its job. How am I going to rewrite the square root of u to make it integratable?
U to the 1/2 power.
And now I can do the power rule, which is add 1 to the power and divide by the new power, which is the same as multiplying by 2/3, which now gets me pi over 27. And that becomes pi over 27, the square root of u cubed. And that becomes pi over 27, the square root of 1 plus 9x to the 4. And we are going to evaluate it at x equals 0 to x equals 4. And I thought I was going to make it, but I'm not. So I'm going to have to keep going now. It's going to be pi over 27. The square root of 416. Goodness gracious me. That's a ridiculous number. 1 plus 9 times 4 to the power of 4, which is the square root of 2305. Take away, well, basically square root of 1, which is just 1. So the surface area there's always a chance that that is simplifiable, but nothing comes to mind, so I'll assume it's not. Are we comfortable with the process that we used? And this is an example of an easy one, right? One that didn't have too much going on. We're comfortable? Any questions?
When we did the 2 lines from the end, when we got pi 27, yes. What happened to the cubed term?
What happened to the
cubed term?
The cube term? Oh, God in Himmel. Right, I'm just leaving that. It's the right answer, but the square root of 2305 cubed. Oh, wait a minute, I could do something. 2305, the square root of 2305. I guess technically I should do that there. I think when I do the next class, I'm going to use a formula that's much smaller numbers. But the process doesn't change because the numbers are ugly, right? I mean, it's still the right process. I think next time I'm going to do it from 0 to 1. That would probably give you much easier numbers to deal with. Yeah, that's the first one. Let's look at a second one. Now we're being asked to take, so this is example 2, a function x equals y squared minus 1 from y equals 1 to 4, but it's still being rotated out the x-axis. So we have to identify which formula that we're going to use. Would you agree it's this guy? Now, where are the clues? Limits integration are in y. X is a function of y, rotated about the x-axis. That's the guy you use in the story. So far, so good. So we've done step one, I've picked it. And my next step is basically taking this guy and differentiating him. Oh, have I ever used the notation x dashed? You know, it just means the derivative of x with respect to y. Right. If you do that, it's easy. Yeah. And if you 1 plus the derivative squared, you get 1 plus 4y squared. And now I'm going to get the surface area. It's the integral from 1 to 4. 2 pi y, the square root of 1 plus 4y squared dy. So far, so good. Right. What technique am I going to use to solve this one?
Would that be a U sub again?
Again, yeah. Either u subs or the thing inside the square root is going to be a perfect square. Right? If you're thinking algebraically, what's the most likely things? It's those. Now, that doesn't mean it's not every situation. You know, there are others, but that is some of them. Picked up some red ink from somewhere. So, differentiate with respect to y, you get 8y. Do the crossover, and then divide. Let's see what that becomes. The integral, stick out the 2 pi, going to have a y, a square root of u, and a 1 over 8y to u. So I now get, what's it going to be? 8. So 8 times 2 is going to be a quarter pi. There we go. The integral of the square root of u du. I'm getting deja vu here, isn't that? Ends up being essentially the same question, at least for the next few lines. So it's going to be u to the half. I'm going to zoom through this bit. U to the 3 halves times a 2/3. 2 cancel. Going to get a 6 pi square root u cubed. 1/6 pi square root of ugly guy. Now we should be able to get surface area. 1/6 pi the square root of 1 plus 4y squared cubed, and it's going to be evaluated from y equals 1 to 4. Can I just dot that? Would you agree it's going to be a rather really ugly cube square root, not that dissimilar to the one that we just did? So far, so good. Right. Any questions before we start looking at some homework question situations? Okay. Let's see, start at the top. There are a couple of questions at the top where you're not actually asked to get the answer, just set up what the integral would look like, right? So let's pick one of these as an example then. Question 1. So in question 1, you have got y equals the cube root of x, and you're going to do x from 1 to 8. Now, if you want to do the integral of this with respect to x, it's going to be the integral from 1 to 5, 2 pi f of x times 1 plus the derivative squared dx. Okay, so if you call this guy 1/3, the derivative is 1/3, right, multiplied by the power, reduced by 1. 1 plus the derivative squared is 1 plus this guy squared. And that's going to be 1 plus 1/9. When you square something, you basically double its power. So it's now that guy. And now when you plug all the pieces in, all they want you to do is to write the integral from 1 to 5, 2 pi, this guy, times the square root of 1 plus 1/9, and I'm looking at their answer. So they're calling it that guy. But actually, you could call it that guy if you wanted. So I don't really think this and that are much better or worse than each other. But that would be all you have to do, right? You do not need to take it any further than that. Okay, few seconds. This is the point where you now put your last name. So you've got a minute. So up to 8:30. So even if you've done it before, just do it again. Okay, let's continue then. This one is an example, question 6. So we're taking the square root curve, which is this guy, and from 1 to 7. Okay. And we're going to get the surface area. So I can look at that formula. I can tell you it's going to be this one. So I'm going to have to call it a half power. That way I can now differentiate it. Multiply by the power, reduce the power by 1. Is there anything I've missed in this derivative? Well, let's phrase it a different way. What have I missed in this derivative? Easy to miss it, but it is missing.
Negative in front of the.
Yeah.
Yeah.
When you differentiate 7 minus x, don't you get a -1? So in other words, the answer is negative. If you do 1 plus this guy squared, you get, no, I won't do it in one go, right? You will get that guy squared. -1/2 squared gets you +1/4. And this guy squared gets you that. Are you happy with 7 minus x, the -1/2 squared gets you 7 minus x, the -1, and that -1/2 squared gets you +1/4. Now we're working on style points. Okay, a -1 power is 7 minus x. I have a 1 plus a fraction. In fact, I'm going to write my fraction again because it doesn't look very pretty. There we go. There, looks nicer now. What do you think I should be doing on my next? What's my algebra goal now? Because that's not where I'm finished. I need better than this. This is still ugly. What could you do with a 1 plus a fraction that might make it a little bit nicer?
Replace the 1 with a fancy one. The 4 parentheses 7 minus x over 4 parentheses 7 minus x.
Agreed. I think there was an example of that same situation that happened when we were doing ArcLand. I think there was an example not unlike this. Right, so what I now have is a single fraction that looks like this. And distribute this, I get 28, take away 4x, add 1. So I now get 27, take away 4x, all over 4 lots of 7 minus x. And that was just to find 1 plus the derivative squared. So the surface area is going to be the integral from a to b, 2 pi f of x, the square root of 1 plus the derivative of f of x squared. So it's going to be the integral from 1 to 7, 2 pi f of x times the square root of this rather messy looking fraction. I'm going to pull the 2 pi out. Right, now we're going to do some unusual algebra. I have a square root of a fraction. Aren't you allowed to take a square root of a fraction and separate into the square root at the top and on the bottom, the square root at the bottom? And isn't the square root of 4 2? And the square root of that guy is 7 minus x. So you might be wondering, why is he doing this? Have another look. Do you see something really nice that has happened? Can something cancel?
Square root of 7 minus x.
And that 2 cancels out with that guy. So we're now looking would you agree that's much prettier than it looked a few minutes ago? Now, if you want to integrate any square root, even one with 27 minus 4x in it, you have to realize that you call it a half power. And I would do the shortcut method, but if you don't want to do the shortcut method, do a U sub, but I would just do the shortcut. And so what would that look like? It would be add 1 to the power, divide by the new power. Okay, what does that negative 4x thing get me? How do we, when we do the shortcut method, what does that negative 4 here get me?
Negative 4.
Or?
Oh,
It's
negative
not-
1 over 4.
Okay. And that we can evaluate at 1 and at 7. Cancel, 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 cancel. Negative 1, 6 pi. But worried about the negative, but I'll figure that out in a minute. 27 take away 4x cubed. Evaluated at 1 and at 7. Okay, if you plug in 7 here, you basically get minus 28 minus 1, and minus 1 cubed is what's worrying me. Anybody see a screw up? You don't want minus 1 cubed inside the square root. Is my
I
limit
think
in?
at the beginning you subtracted the 1 from the 28 instead of added it, so it should be 29 minus 4x.
Oh,
It's on
should
the
be-
first page.
okay. Where did I go wrong? Here. 28, add 1. There we go. 29. Thank you. This is one of the easier fixes because it doesn't affect anything else. Now I'm happy because I get 1 cubed and the square root of 1 is 1. And then if I plug 1 in here, I get 29, take away 4, which is 25. So take away the square root of 25 cubed. And you get -1/6 pi, 1, take away 5, and 25 times the cube root of 5. Oh, that's a really nice number. It's 125. And so that's -124 over -6 pi, which is positive. Right. And positive what? 2 would work. 62/3 pi. And it's the right answer because I got the answer to the side here. That's a lot of lines, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9. About 19, 20 lines of working. Not your 5-minute question then, right? See if we can get something even weirder for our next one. That's another square root. I think I've done a square root. This one is like question 9. And the curve is going to be the cosine of 1/2 x. And it's going to be from x equals 0 to, what they got? 3, by 3. I'll make it 1, make it easier numbers. And it's about the x-axis. Right, so putting this guy together, we know that we are going to be using the top formula again, which is what I'd expect, right? Everything in x's. So I'm going to start with this fella. And I'm going to differentiate this guy. Well, if you differentiate a cosine, you get a negative sign. Since it's a chain rule, you get a half. So you get -1/2, the sine of 1/2 x. If you then 1 add its derivative squared, you get that guy. And so you get 1 plus 1/4 sine squared of 1/2 x. And I could, I guess, try and play about with that, but let's not. Let's just leave it alone. So the surface area should be the integral from 0 to 1. 2 pi cosine of 1/2 x square root of this guy dx. That integral there is sneaky but nice. Why is it sneaky? None of the obvious u subs work, but it is nonetheless a u sub. What u sub do you think you would use to get this integral? The obvious one would be everything inside the square root, but that doesn't work.
Would it be just sine 1/2 x?
Correct. What made you think that?
To cancel out the cosine x?
Right. Have you noticed that sometimes when you do u subs, the thing that you choose the u sub for is to get rid of something else. So the reason you pick the sine x is because you know it's going to get rid of a cosine half x. And you can sometimes use that trick when the normal rules of what you should typically pick for a u sub just don't work. Now, if you differentiate the sine of a half x, you get the cosine of a half x, right, times 2, which I'm just going to write that way. You do the crossover, you get that fella. And then if you divide everybody by the cosine of a half x to isolate the dx. So we have now got a reasonable chance of doing this fella. It's going to be the integral. Let's kick out the 2 pi. Cosine of a half x times the square root of u times 2 over the cosine of a half x, the du. And these cancel out, and that gets you 4, and I'm getting a really annoying, I can't seem to avoid getting square roots of u's in questions. I was going to make that the last question until I realized that that's where it went. So can we just dot that, because you've done 2 just like it. And let's see if we can find something that isn't a square root of u. At least is not a square root of u and just that. So who else can we go for? Ah, perfect. I don't know if I'm going to get this guy finished all the way to the end, but I'll try and get as far as I can, and then we can just talk about, you know, what you would do to finish it.
What did you do with the 1?
Say again?
What did you do with the 1 on the previous question?
Okay, what did I do with the 1? This question here?
Yeah, what did you do with the 1 when you did the u, since you didn't do the full?
Oh, it's 1 plus u squared. Whoa, rewind. That question's worth doing now. It's 2 pi, the cosine of a half x. It's not u, which is what my brain was thinking. It's 1 plus 1/4 u squared, 2 over the cosine of a half x. So it is worth doing. So I've got 4 pi, the integral of the square root of 1 plus 1/4 squared du. Okay. Are you, oh, my screens went weird. Are you still seeing this? Yes, you are. Good. This crops up from time to time, that you're going to have an integral. I could do this integral. It would be a half tan theta, but I don't want to. And if I did do a half tan theta, it actually turns into a version of secant cubed theta, which was one of the homework questions. If you look this guy up, there will be, in the back of the book, an integral that looks something like that guy. In other words, what you do is you just look up a standard integral for it. Now, I've got about 4 minutes. I'm going to see if I can find that integral. Has anybody used the standard integrals at the back of the ebook yet? Right, so this is going to be brand new for everyone. Okay. Let me see if I can get into WebAssign's ebook without too much trouble. Check it out. So, you know, oh God. Remember we did secant theta, and I told you it's just a standard integral, right? And I told you it was the log of secant theta plus tan theta. Remember that one? There are lots of little weird integrals that we don't expect you to memorize, but we also don't expect you to do them from scratch, because can you imagine an X sub might take you another half hour on top of a question that's just taking you 20 minutes to do? It seems if there's ways around it, we can. So I'm looking, I hope you're looking at this guy here. Are you looking at the textbook? Ebook? I can't see any notes here.
Yes.
We are doing it, okay. I'll just try and make it a little bit bigger. And I'm going to see if I can find where they have numbers like number 21, number 50, and so on. I'll see if it's under appendix. If somebody has found it before, then tell me. No, that's not my issues, that's just answers. So it's not there. Okay, let's go back home. Get another way of looking at it. I've got a different version of the book. I can hopefully find it that way. Come on. Index. A143, okay. How do you get to A143? Scroll it down. Here we go. Ah! Darn it in space. I had it. And then I moved it. Got it. Okay. Where the heck is this now? Here. What? I'm going to take a copy of these things and just put them in Canvas because they are a pain to find. And I'm just going to show you where they are. Once I get out of this window and show you the guy. I use now looking at reference page 10. Do you see it? Is that what you're saying? Okay. Let's see if I can make it. This is a PDF. So I should be able to just slide it, make it bigger. Right. Now, the guy we're looking for is, well, let's put some other guys. If you wanted to find out what sine cubed u is, do you see it's that guy there? Do you see how these work? But that's not the guy we're looking for. So I want to find I want to find a square root that's not 1 over somebody. Okay. And which ones have we got? I want a 1 plus a u squared. So that'll be like a u squared plus 1 kind of look to it. There we are. This guy called number 21, do you see it's the square root of a squared plus u squared? You see that get there? Right, you can, the guy that we're looking for is not quite him, but he's the one that we're going to use. We want 1 plus a quarter u squared. Okay, so what am I going to do is I'm going to leave that guy and show you how you make him look like the fella in that table. If you take 1 plus 1 quarter u squared, if you pull out 1 quarter, you get 4 plus u squared. That gets you 1/2 the square root of 4 plus u squared. And that is the a squared plus u squared that they just had. And then you just write down what number 21 does, and you make a 2, because 2 squared is 4. Sorry for rushing that last bit, but that's essentially how you get round finding ugly square roots at the end of your day when you're finished. Okay, now before I forget, I'm going to take a snapshot of this piece of the picture and put it on Canvas for you. Okay, that's us. Time's beat us. Bye-bye, guys. See you tomorrow. I'll hang about for a few questions.
Can you move the last page up a little bit? I can't see the last few lines.
There we go. Now, I'm trying to figure out how to take just a couple of pages from my PDF. Come on, don't be protected. You should be able to let me do that. Okay, if we get any questions, I don't have enough time to copy that thing right away. I'll have to wait till after my classes, but I will get them on Canvas eventually.
Can you show me how number 6 ended? I didn't get to see that part.
I noticed you get booted out.
I did. The transformer blew.
Oh, did you hear a pop sound or a bang?
I didn't, but my dad did.
Okay. It finished here. And that one is actually correct. It's checked against the solutions.
And then can I see the beginning of number 9?
Number. And here's the ending 9. Actually, now I'm thinking about that, I should have probably did a half sine a half x. That would have came out much prettier. But too late now.
Wonderful. Can I see the first few lines of that problem? Got it. Thank you.
Okay, bye-bye. I'll see you tomorrow, or maybe in office hours.
Thank you.